Swayam Prabha. Digital India. Educated India.
So, next we are going to discuss the GCD and LCM, right? GCD and LCM. Definition: both the numbers A and B as several divisors. It is a common incidence that they have some same divisors, but the greatest one among them is unique numbers. Then one is called the GCD or greatest common divisor or highest common divisor of A and B. This is frequently denoted by the GCD of A comma B or HCF of A comma B. Sometimes it is denoted shortly by A comma B only. In this note, we shall use the notation for brevity that when ordered pair of A comma B equal to 1 is a GCD of two numbers equal to 1. That is, two numbers do not have a common divisor other than 1, then A is called to be a co-prime or relatively prime with B and is denoted by A perpendicular B. So, keep it in mind this statement so that you can understand the GCD. For example, you take 6 and 28 and 6 having 2 into 3 and 28 having what that is 2 into 14. 14 can be written as 7 into 2, right, and then so the GCD of this is 2, right, because 2 is the most common part of among them, right, and therefore this is having the GCD is 2. Similarly, you take 56 and 243, but it does not have a common factor other than 1, therefore it does not having the GCD other than 1. Next, the smallest positive integer is divisible by both A and B is called the least common multiple of A and B, that is LCM of A comma B or the square bracket A comma B, and it is denoted by the least common multiple. For brevity, we shall use the notation closed interval A comma B stands for the least common multiple of two numbers. For example, if you take 24 comma 40, so the LCM of 24 comma 40 is 120, right. Next, properties of GCD and LCM. If the GCD of A comma B divides A and the GCD of A comma B divides B and A divides LCM of A comma B, definitely B divides LCM of A comma B. If LCM and into GCD of two numbers, so that the LCM is always greater or equal to the GCM. If D divides A and D divides B, then D divides AB, because AB is greatest among the factors of A and B. So, keep it in mind this basic properties. So, every prime divisors of A and B divides the GCD of two numbers A comma B. So, every prime divisors of the GCD of A comma B divides A and B. Suppose the GCD of two numbers, you take it, divides the linear expression Ax plus By for any integer x comma y. This actually a corollary of divisibility property of this number 7, this property is number 7. And also make a note of this, if A is equal to the GCD of A comma B is A into A dash, and B is equivalent to the GCD of A comma B into B dash, definitely A dash divides B dash. This is very easy to sense that since the GCD of A comma B is the greatest among the common divisors, if A dash comma B dash shares the common divisor, say D, then this would contradict the maximality of A comma B. Otherwise, we could multiply D with A comma B and it would be yield the GCD of greater than A comma B, namely D into the GCD of AB is thus D equal to 1. And ninth one, the GCD of A comma B is A, and AK comma BK is K into A comma B, we can write. And the GCD of A comma 1 is equal to 1, and the GCD of A comma 0 is A. So, these are all the properties. Further, in the division algorithm, B is equal to AQ plus R, right, and the GCD of A comma B is equal to A comma R. Suppose 4 divide 3, then 1 times of 3, remainder is 2, then 4 can be written as 3 into 1 plus 1, right. Here this is B, and this is a quotient, right. This is the divisor and this is the remainder. Therefore, the GCD 3 comma 4 is equal to the GCD of what, A comma 1. So, this is AB and this is AR. So, it will definitely comes. So, from the divisibility, if B, that is the GCD of 3 comma 4 divides B, B is what, here B is 4, right, then definitely this can be written as what, AQ plus R. So, it holds good for any number. If divisibility comes, then the A comma GCD of A comma B divides AQ plus R minus, we can write A into Q, which is equal to R, because you bring this side, therefore, we can write like this. So, we have the GCD of A comma B is equal to GCD of A comma R. Now, we have some special cases. You take A. So, this is here B equal to 4, A equal to 3, R equal to 1, Q equal to 1, A is 3 and 3 plus 1 is 4, and definitely the GCD is 1. Similarly, 3 comma 3 plus 4 you take it, which is equal to what, 3 comma 7, and this is also the GCD and this GCD are same. This is 1 and 3 comma 4 is 1, therefore, this is also holds good of GCD of two numbers. And A is greater or equal to the GCD of A comma B, because you take 3 comma 4 as 1 and 3 is always greater or equal to 1. And similarly, B is always greater or equal to A comma B, mean 4 is greater or equal to 3 comma 4, which is equal to 1, 4 is greater or equal to 1. So, this is holds good like that. And similarly for LCM of A comma B is greater than or equal to A, and LCM of A comma B is greater than or equal to, the equality occurs in the previous two inequalities if and only if A equal to B is true. For a prime P, either the GCD of P comma A is 1 or A comma P equal to P. Since P is a prime, P divides A or P does not divide A. So, A divides P when P does not divide A, and the GCD of A comma P equal to P when P divides A. If A is perpendicular to C, means A is equal to A comma BC, you take it, the GCD you take it, and this GCD you take it, both are same. So, say 2, 3, 5 you take it, 2 comma 5 is equal to 1, and 2 comma 3 into 5 it becomes 2 comma 15. See, this is also 1 and this is also 1, therefore, this is true. So, this is true because C will not share any common factor with A. So, the GCD would remain unchanged. So, the 15 does not have a common factor with 2. So, this way we can express the value of 15. If A divides BC with A is perpendicular to C, comma A divides B. So, according to the corollary, if A divides C and B divides C, then the least common multiple of AB divides C in general, A1 comma A2 and so on, AN divides N, and the LCM of A1, A2 and so on, AN divides N. So, this is the most general form of what the GCD and LCM of the numbers. So, according to the corollary 3 says that if A1, A2 and so on, AN divides N, then A1 to AN pairwise co-prime integer, then A1, A2 and so on, AN divides N is true. If M is a positive integer divisible by both A and B, then the least common multiple by divides M, and M greater or equal to the LCM of A comma B. A very important theorem says that if the product of GCD of one number into product of other number will be the product of a number, A comma B one number, and you take GCD and LCM of that number, we have the product of numbers. So, we shall prove this only using the definition of GCD and LCM or to make a better sense. Therefore, according to the definition, the LCM of two number is greatest common part of A and B. Other hand, A comma B contains both common and uncommon part of A and B. Thus, the GCD of two number include in AB, and then we have what we have a common factor left except A comma B. Therefore, A equal to A comma B and into UA and B equal to A comma B into UB. It follows that what closed interval A comma B equal to A comma B into UA into UB. Therefore, A dot B into closed interval A comma B is equal to AB whole square into UA UB from these two. So, that AB is equal to AB the whole square into UA BB, hence it is proved. So, this way we can prove that important theorem of the product of what GCD and LCM. If A is perpendicular to B, mean the greatest common divisor of two number, then A power m and B power n is a GCD of one another for positive integer m comma n. If A divides B, then ordered pair of A comma B equal to A. Now, based on that, we have usual identities in divisibility, right. So, let us have the identity 3, Sophie-Germain identity, mean if you take A and B or two number and then power 4 multiply with the 4. So, A power 4 plus 4 power B power 4 is equal to what? A square plus 2AB plus 2B square into A square minus 2AB plus 2B square. So, using these ideas we have the inequalities, keep it in mind. If both A comma B greater than 1 and A power 4 plus B power 4 is a product of at least two numbers greater than 1, definitely A power 4 plus B power 4 is composite, right. So, the only case when it is prime, if A comma B equal to 1, then A power 4 plus B 4B power 4 is 5 is a prime. So, you have to take A comma B is greater than 1, right. So, first A power 4 is 2 power 4 which is equal to 16, and then B power 4 is equal to 3 power 4 which is equal to 9 into 9 is 81. Now, we have what? A power 4 plus 4 into B power 4 which is equal to what? 16 plus 4 into 81, right. So, this is a product of least common integer greater than 1, right. You see, all are divisible by 2, therefore, it is a composite. So, this case is true for greater than 1. If A comma B is 1, then it becomes 5, 5 is a prime, except that everything it will be true for this equality is called it as Sophie-Germain identity. Next identity for any positive integer n, A power n minus B power n is A minus B into A power n minus 1 plus A power n minus 2 and so on B power n. Already we proved in mathematical induction, and it will be very useful for using this identity. And next corollary says that A minus B exactly divide A power n minus B power n for all n in n. If n is odd, then A power n plus B power n equal to A power n minus of minus B power n, because minus B whole power n is minus of B power n, minus and minus plus, therefore, A power n plus B power n will come. Thus, A power n plus B can be written A plus B into this term, A power n minus 1 plus A power n minus 2 and so on, B power n minus 1, and definitely the RHS of the above term divides A plus B, therefore, this term divides one another for all odd n. Next identity, A power m minus B power m comma A power n minus B power n can be written as A power of the GCD of two numbers minus B power of GCD of two numbers. So, you can take what any A is 2 and B is 3 like that, 2 m equal to what, some number 2 and n equal to 3 you take it, and A is also this. So, 2 square minus 3 square you take it, comma 2 square. So, 2 square plus 2 square 3 square here, 2 cube in my minus 3 cube you take it. So, 4 minus 9 here, 8 minus 27. So, it become minus 5 comma 19 minus 19. You see this is nothing but A. A is what, 2 power 2 comma 3 minus B. B is what, b is 3 power 2 comma 3. So, the GCD of this one is 1 1 2 minus 3 equal to 1, exactly we can write like this. So, we can do with the help of this identity, we can do that. It is relatively prime numbers. If two non-zero integers a and b are said to be relatively prime, the GCD of two numbers equal to 1. Another example, if 12 and 35 are relatively prime because they have a common factor. 12 can be written as 4 into 3 and 35 can be written as 5 into 7. Now, you see they have no common factor and other than 1, therefore, the common factor is 1 only, therefore, 12 and 35 are relatively prime in the GCD of two number equal to 1. Whereas, you take 12 equal to 4 into 3 and 15 you take 5 into 3, therefore, they have a common factor 3, therefore, they are not relatively prime. So, like that we can do for relatively prime numbers. Next, if p is a prime, a belongs to integer, then the only positive divisors of p are 1 and p, and hence either the GCD of a comma p equal to 1 or the GCD of a comma p equal to p. The first case a and p are relatively prime, the second case p divides a. So, when p is a prime, either the GCD of a comma p equal to 1 or p divides a. So, this way we can note the point of relatively primes to one another. Next example, 4 and 6 are not relatively prime because they have a common factor. So, 4 divides 60 and therefore, 10 into 6, but 4 does not divide 10 and 4 does not divide 6. Suppose the GCD of two numbers equal to 1, that a divides BC, then a divides C. The proof is very simple. Since AB the GCD is 1, so there exists a two number s comma t such that 1 can be written as AS plus BT. Since A divides BC, there exists n in Z with BC equal to NA, thus C equal to C into 1. Therefore, instead of 1 we can write C into AS plus BT. So, multiply them, A into SC plus BC into T. Therefore, A into SC plus BC can be written as NA. Therefore, A into ST plus NT is a multiple of A. So, this way we can prove what A divides C. Next corollary, let P be a prime number. Suppose that P divides AB, then P divides A or P divides B. So, if P divides A, we done it. Otherwise, if the GCD of A comma P is 1, according to the previous theorem 2.5, P divides B. So, if P is a prime and P divides A square, then P divides A. So, P equal to 2, right, is a prime, and A equal to 3 you take it, right, A equal to 3, that is A equal to 3 means 9. So, P does not divide A. So, if P equal to A equal to some 4 like that. So, what I have to do is 4 can be written as about 2 square, but therefore, this is also not true. So, you have to take A as some number should be divided. Say for example, A equal to 6 you take it, and then A square equal to 6 square equal to 36, then P is 2 divides A a square equal to 36, right. Definitely P 2 divides 6 is true. So, like that the possibilities of this number is true. So, what you can infer, if P equal to 2, suppose that AB equal to 6, that is 2 into 3, then 2 divides 2 into 3 implies 2 divides 2. So, this is also true. So, two corollary states that for following up the corollary 2.6 we can develop corollary 2.7. If P is prime and P divides A square, then P divides A, take A equal to B, right. Therefore, in substitute in corollary 2.6, so that we have a 2.6 corollary holds good. Next example 2.8, of course, the corresponding statement for the composite numbers is usually false. For example, 12 divides 6 square, but 12 does not divide 6. See, 12 divides 36, but 12 does not divide 6. And corollary 2.9 says that if P is a prime number, suppose A1, A2 and so on, An are integers, then P divides the product of the numbers. So, if P equal to 2 and A1, A2 and so on, An, say for example 2 into 3, right. So, 2 into 3 into 5 and so on, then P divides 2 into 3 into 5. So, definitely one of the numbers of this it divides, that number should be less than n. So, here n is equal to 3, right, and I equal to 1, therefore 1 less than or equal to 3. So, that way it will be is true for the corollary 2.8, but now let us prove the statement of corollary 2.9. We prove by induction when n is greater or equal to 2 square. In this case, n equal to 2 is precisely corollary 2.6. Suppose the result is true for n is greater or equal to 2, and we again n plus 1 integer of a1, a2 and so on, an plus 1, that P divides a1, a2 and so on, an plus 1, take a equal to a1 to an and b equal to an plus 1 in the corollary, it follows that P divides a1, a2 and so on, a1, or P divides a plus 1. Therefore, by inductive hypothesis it follows that P divides a for some I less than or equal to n, or P divides an plus 1. So, next corollary, if P is a prime number and P divides a power n, definitely P divides a. So, we have to prove with the condition that a1, a2 and so on, an equal to a. According to corollary 2.9, we can easily prove it. So, up to this the first model of this unit 2 is over.